días a todos, muchísimas gracias por unirse a este panel de estimaciones agrícolas. Mi nombre es Esteban Copati, yo soy jefe de estimaciones agrícolas en la Bolsa de Cereales y antes de comenzar con el set de presentaciones, quiero hacer una breve introducción para comentarles cómo va a ser la dinámica del panel. Se ha tomado la decisión de que como dos de los speakers son americanos, el panel va a ser enteramente grabado en inglés, pero no se preocupen porque va a estar subtitulado. Belén, una de las investigadoras invitadas en el día de hoy, es española. Ella va a presentar su trabajo de investigación en castellano para que no se pierdan ningún detalle de su investigación, pero la interacción entre nosotros va a ser enteramente en inglés. Y por último también vale la aclaración de que Jordan, el primer expositor, vive en Australia, y dada la gran brecha horaria que hay entre todos los integrantes de este panel, era muy difícil fijar una fecha común, un horario común para grabar, y aparte Jordan tenía una agenda realmente complicada porque se estaba yendo de vacaciones, así que su presentación fue previamente grabada. Okay, let's switch to English. Hi Belén, hi Mike, how are you doing?
Hey, how are you? I'm good. And you?
I'm fine. How you doing, Mike?
Great, thank you for having me here.
Thank you for participating in this panel. I was telling the audience that this panel is going to be entirely in English, so this way we can interact more fluently among each other. Okay. Before starting with the presentation, I would like to share with the audience some ideas and goals of this panel. When I started to think about this agriculture estimate panel, I thought that it was going to be interesting to share with the audience how colleagues from different parts of the world are working in the development of new technologies that help us to improve the assessment of key variables on a large scale in the agricultural activity. Each speaker is going to explain the audience how they are working with remote sensing techniques to assess key variables of our work. They are going to talk about planted area, weather and crop condition during each season, and finally year forecasting models. Each research project is going to be presented by its lead, and this is important to clarify also. Okay, let's start with the first speaker. Jordan Graesser is going to talk about estimates of land use between 1999 and 2019. He's going to talk about 20 years of agriculture in Argentina. As I told you before, his presentation was previously recorded, so let's pay attention. And before starting with Jordan, let me introduce you. Jordan Graesser is a senior research officer at the University of Queensland, where he specialized in land change science and remote sensing. He's interested in the spatial temporal analysis of agricultural landscape patterns and trends, as well as estimating crop area and rotation with remote sensing. Since 2016, he has worked on a land use cover mapping project across the Southern Cone with colleagues from INTA and also from the Buenos Aires Grain Exchange. He received his PhD in 2016 from McGill University, where he studied the changing scale of agriculture across Latin America. Okay, let's pay attention to his presentation.
Hello. First, I would like to thank Esteban Copati for inviting me to this session. And before I begin, I just want to acknowledge all the collaborators on this work who are listed at the bottom of this slide. And they're representing Boston University, Grains Exchange, INTA, and INIA from Uruguay. With this work across the Southern Cone, the overall objectives are to use Earth observations to estimate long-term land cover, such as cropland, and short-term land use, such as crop species rotations, and the changes over those time periods. We're focusing on the Southern Cone, which typically might not include Bolivia, but our study region includes the countries listed there, which I'll show you results of later on in the talk. This work began in 2017 when a colleague from Boston University and I first visited Argentina to collect data on land cover and crop types. We followed this work up with more data collection across Argentina, including, in addition, Paraguay, and as well as face-to-face meetings with Esteban at Grains Exchange and folks at INTA. And then the last few years, we've been processing the field data, producing land cover maps over a 20-year period, and developing methods for crop type mapping, all of which I'll show in the following slides. So I mentioned the field data. This is a collaborative effort from all of the institutes listed at the top of the slide. There's two components with this work. One is land cover, the other one being crop species mapping. With the land cover, we're looking at dominant land covers. So for example, cropland or tree cover. The crop species work, we are attempting to map mainly the major crops across the region. Of course, this list is not exhaustive of all the crops that are grown across those different countries, nor is it exhaustive of all the crops that are in our database. The overall workflow of our process begins with the field data. And I mentioned Earth observations. We use Landsat data dating back to 1999. And we process those data by first reconstructing weekly time series and then segmenting individual field parcels. And I'll explain these in detail in a bit. And those data then feed into a framework where we use sequential modeling, which allows us to estimate annual land use and land cover on a field level. So I'll briefly explain these methods, beginning with the time series work. So we've developed this method called dynamic temporal smoothing. So here we're looking at two different fields from central Argentina. We have time on the x-axis beginning in 2010 and a vegetation index from Landsat on the y-axis. And there's three different Landsat sensors shown here over that time period. You can see in some periods there's sparse data gaps. And those are could be caused by cloud cover, for example. So with this work, the goal here is to reconstruct what the phenological curves would look like by reconstructing weekly time intervals in order to have gap-free data. And this allows us to do very precise mapping for crop types, where we can then estimate planting and harvesting dates down to the weeks, for example. I mentioned we do field segmentation. So this is work that we introduced several years ago. We've made enhancements and modifications to the work. The overall goal here is to delineate biophysical boundaries of crops over a 12-month or year and a half time frame. We're looking, as I said, we're looking at individual crops. So we're not looking at things like tenure, for example. And then in the modeling framework, we use this graphical models or sequential models that are called conditional random fields. Now these models are supervised classification. So this is where our field data comes in. So like all supervised classification, you need example data, and those would be our labels. So this could be land cover, or it could be crop types. And these models work over time. So each one of these vertical nodes represents a year in the process. And the features could represent anything from the individual Landsat bands or derived indices. And what this graphic is illustrating is that there are codependencies in land cover transitions, and those codependencies are captured and modeled in the predictions with this modeling framework. So these models are really useful for estimating sequences of data, but it's really difficult to collect data over repeat periods because of missing data or cloud cover. So we've set up a sampling framework to try to address this. We work on a grid by grid basis. So in this example, we have a grid in Cordoba. And our grids are 150 kilometers on all sides. And from the center of that grid, we sample all of our field data within a given radius. So the field data here are shown in the color gradients, and the different colors represent different weights that we give each sample based on how near they are to the grid center. And we will take all samples within the radius. Here, a 250 kilometer radius is used. We might expand that search if the sample pool is not satisfied. We have a collection of data and these range from mid-2000s to present day. But these are all static snapshots, if you will, of the land cover crop from that point in time. So in order to train a conditional random field, we generate random sequences by a process that we call temporal augmentation. But here we have two examples where we've created synthetic data so that where we have our weekly smooth data on the axis here, and we have 20 years of simulated data. So each year in the simulated sequence comes from a field data point from any point in time, but the order is completely random. So here we've just generated a fake transition of tree cover to herbaceous. On the right, we've done the same with the herbaceous crop and wetland rotation over a 20-year period. And by doing this thousands of times, we provide essentially every possible land cover transition for the conditional random field model. So then when it sees a real-time series sequence with the Landsat data, it's able to make land cover predictions. I'll show you some of the results from that work here. We have the two endpoints from our land cover work beginning in 1999 on the left and 2018 on the right. And these are the broad land cover classes. And I think of most interest to this audience is probably the cropland, which is illustrated in orange. And over that time period, you can see, for example, the expansion of cropland in the Pampas, as well as expansion in northern Argentina and eastern Paraguay. But as I mentioned, these models are really most useful for sequential mapping. And so we applied these over a 20-year period. So if we zoom into an area in the Pampas in Argentina, we can see the predictions over this time. And these models produce very stable predictions. And by stable, I don't mean we're not predicting land cover. You can see that the model's estimating an expansion of cropland in this example. But we do not see year-to-year pixel flipping, as it's termed in the remote sensing community. As another example, moving farther west in Argentina, again, we have both expansion of grasslands, probably pasture land, as well as cropland. And here we have cropland expansion into tree cover. So not only are these data from Earth observations useful for quantifying the area of our land cover, they're also useful for looking at long-term year-to-year land cover transitions. So I just mentioned quantifying area. And one thing that we want to do with this data is quantify cropland changes over time. But the data from the land cover represents the total land use for cropland, not accounting for multiple crops grown over a 12-month period. So in order to estimate planted area of cropland, we need to take into account the phenology or the phenological cycles. And that's where the time series work comes in again. So we use the phenological cycles to count the number of crops grown over a 12-month period. To illustrate this process, we have a graph where we have time on the x-axis over a 20-year period and area on the y-axis. And I'll have you first focus on the orange line here, and that's the estimated area of planted cropland by INTA. And then we have the green line, the same planted area estimates, but estimated by Grains Exchange. And if you jump down to the bottom line in pink, those are our estimates based on Landsat of the total cropland footprint, not accounting for crop cycles. So once we account for the number of crops grown over the 12-month period, we obtain the blue line, which is our planted area estimates from satellites, which are much more closely aligned with the INTA and Grains Exchange numbers. Another way of looking at this data and looking at the benefit of using Earth observations for this type of work is to look at expansion and intensification. So we have the same axes, area and time, and we're looking at our Landsat-based estimates of cropland area and planted area. So we have cropland, the land used for cropland shown in the pink line, and then the blue line we have the planted area. And instead of looking at the area over time, we're looking at the change in the area. So we see from the early 2000s, while there was still expansion of both, the rate of expansion declined up until around 2012. And around 2012, we know that the expansion of cropland was relatively simple by our previous graph, whereas the planted area continued to increase. So we have a period of intensification. When we compare our results from the Landsat planted area estimates, which is shown on the x-axis, against the INTA planted area estimates, which are shown on the y-axis, for some of the key provinces for agricultural production in Argentina, at municipality scale, so each point is a municipality in the provinces listed in the legend, we see pretty good agreement between our estimates and the INTA estimates. We tend to underestimate in the drier regions. So some of these green points here in the lower scatter, for example, are municipalities in southern Buenos Aires. The last topic that I want to discuss is some of the work that we're doing on crop species mapping. So we did some prototyping for in-season crop mapping for the 2017-18 period. And the first thing you'll probably notice in this graph is that the estimates on the inset on the right are done at the field level, whereas the land cover estimates are produced at the pixel level. So here we've taken the data from the 2017-18 period, fit a conditional random field model, and estimated for the same period. And we have estimates of soybeans in shades of green and maize in shades of yellow. If we move east across the river, we see a little more diversity in different field sizes, but also different crops. So here we're also estimating crops such as sorghum, millet, and alfalfa, for example. So to date, we've only done this work for this single season, which is because most of my focus recently has been on estimating crop rotations, which I think in relative terms to in-season crop mapping is a more challenging problem. So I'll just show you briefly some of this work. So using that same framework of generating thousands of random sequences to train a model, we replaced the land cover work that I showed earlier with crops. So here we can generate a sequence over a short period, about 6 years, of a winter crop cycle. And again, the order and the sequence is completely random, whereas the individual slices for each year come from real field data. So we can generate a sequence where we see fallow and barley and spring wheat combination. And on the right, we have this similar sequence, except for a summer crop rotation. And using these data to fit a conditional random field model, we can then predict the crop type for each season. So here we have a 10-year time period with EVI on the y-axis, and at each crop cycle, so each approximate season, so these are not exactly 6-month intervals, we estimate the winter crop here as estimated. For example, this is the model estimated spring wheat for this cycle, followed by the summer. And we do this for every winter summer crop cycle over that 10-year period. So I think this work is really promising. It's still pretty early. We're in the early stages of this, but I think there's a lot of promise for scaling up and doing longer term crop type mapping. To wrap up, some of the challenges that we're facing, especially with this crop species work, is doing a proper assessment. Because we don't have repeat samples, it's difficult to have an unbiased assessment of how well we are doing. We can always assess withheld samples from our models, but I think it's key, moving forward, is probably key to do an unbiased assessment over time. I mentioned the planted versus harvested estimates. Because the samples are collected at a single point in time and not revisited, our models are currently not able to predict things such as pest outbreaks and drought. And then finally, because this is largely developmental work, we're using local high performance compute infrastructure, so there's runtime and storage costs associated there. And then lastly, to conclude, it's my final slide, where we are headed. In the next month or two, we'll be doing an unbiased assessment of the 20-year land cover estimates that I showed earlier. We're publishing the work on the methods that I presented. And then lastly, hopefully seeking funding to continue expand this work. I think ideally would like to update the annual land cover estimates, potentially expand the crop species mapping to a larger scale, and then ideally make the data publicly available. So with that, again, I'll thank Esteban for giving me this opportunity. Thank you for your attention. Again, want to acknowledge all the collaborators and their respective institutions, and please contact me if you have any questions or ideas. Thank you.
That was Jordan Graesser presenting his work, and at the end of his presentation, I asked Jordan, what happened when a plot suffered a flood or a drought in the middle of its phenological cycle, and how does his model classify it? This is important to better understand if he's mapping planted area or harvestable area. His answer was this one.
Yeah, so I think the two components of our work are key. So the land cover work is only estimating cropland area. So we're not estimating planted or harvested area there. With the crop type work, I think we can get much more closer to defining the two. But with the crop species mapping, we're estimating planted area because, as I mentioned in my talk, we're not necessarily estimating what's happening at the end of the time series sequence. We're just estimating the crop cover over a period, over a 6-month period or 12-month period. So in general, we're estimating planted area. I think there's potential to estimate harvested area, but at this point in time, our methods are not doing that.
And finally, the second question I asked Jordan was, what does he think about the future of these remote sensing technologies applied to agriculture? Where are these technologies heading? And these were his comments.
Yeah, thank you. That's a wonderful question. I think the road down the future for remote sensing in agriculture is really exciting. You see all these new technologies and new sensors coming in. So we have new Sentinel data from the European Space Agency, all this planet scope imagery at sub 10 meter. I think it's opening up a lot of new research avenues for a lot of people. So I think we'll be seeing a lot more of like deep learning approaches. We're seeing a lot of groups and individuals attempting to estimate and delineate field boundaries across the planet. A lot of this work is being done in industry, I think, so we probably don't see a lot of that work that you might see from a university, for example. In terms of other work that I've seen, especially related to planted area estimates and cropland, rotations and phenology, for example, folks at University of Maryland are doing some exciting stuff, especially estimating commodity crops. I think they're doing some soybean mapping across South America. European Space Agency, which I believe the work is led by Peter de Fourny in Belgium on the Sentu Agri. They're showing really nice examples of deployable agricultural mapping across anywhere on the planet. The work that they're doing is really, really neat. I think in the future, with higher temporal resolution and higher spatial resolution, we're going to see more research questions get asked and more applications in regions across the planet, such as sub-Saharan Africa and South Asia, where agriculture is just very difficult to characterize on a map from a remote sensing perspective. But I think these new technologies are opening up doors to improve data there.
That was Jordan Graesser presenting his incredible work. There is no doubt that the result of his research project is going to represent a huge contribution for the agricultural activity to our country. He's analyzing 20 years of agriculture and maybe the 20 main interesting years, because during that period we registered an important expansion of our agricultural region, but also because during that period we also incorporated a lot of technology that changed the way we produce fruit on a large scale in Argentina. He, as results of his research project, he will be able to answer questions such as, for example, the average size of the plots in Argentina on a national scale or in a regional scale, the development of the entire crop area during those 20 years, for example. And also the rotation of crop, which is a key variable in terms of sustainability for food production on a large scale also. But up to now, we've been talking about planted area, and now it's time to talk about what happened with the weather. You know? Once we have our planted area estimated, we have to pay attention every week to what happened with weather condition and how the weather condition affects the crops on the field on a large scale also. So we are lucky because we have here Mike Humber from Maryland University. Mike is going to talk about, is going to present the GLAM system and great tool that become part of our day-to-day analysis at the Grain Exchange. Let me introduce Mike to you. Dr. Mike Humber is an assistant research professor at the University of Maryland. He's the data lead for the NASA Harvest Consortium for Food Security and Agriculture, and a member of MODI's and BEER's Burned Area and Active Fire Science team. He holds a master's degree in Geospatial Information Science and a doctoral degree in Geography. Dr. Humber has led the development of several web mapping applications, including the GeoGlam crop monitor for AMIS and early warning, and the cloud-based next generation global agricultural monitoring GLAM system, and the NASA Harvest portal. Hi, Mike, how are you doing?
Great, thank you again, Esteban, for having me here.
Okay, I'm so happy that you are here in this panel with us, Mike, and you can start with your presentation now.
Perfect, thank you. So as Esteban mentioned, I'm Mike Humber. I'm from the University of Maryland and the NASA Harvest Consortium on Food Security and Agriculture. And today I'm very happy to talk to you about the new GLAM system that we've put together. So this is the Global Agricultural Monitoring System. And specifically today, I want to focus on some of the crop and weather condition monitoring tools that we have within the system so that hopefully this will create some interest in actually going and checking the variables to see if they match with what people's assessments are of the conditions on the ground and hopefully find some of these information sources useful. So Esteban had mentioned a little bit about myself. I am Mike Humber, again from the NASA Harvest Consortium. I'm the Data and Harvest Portal Lead. I'm also an assistant professor at the University of Maryland in the Department of Geographical Sciences. Currently, I work on several projects. The ones that are most relevant to what we're talking about here are this mapping national scale agricultural project practices, which we're working with the Grains Exchange in partnership with. We are also looking at some of the impacts of the current pandemic on agricultural production and trade, and then more relevant, also the GLAM system and how we built this prototype and implemented this system in the cloud in order to provide data in a faster, more efficient, and hopefully more useful way. And for that project, I'm the lead Amazon Web Services developer. A little bit about NASA Harvest before I get started. NASA Harvest is a program meant to improve the awareness, use, and uptake of Earth observations from satellite-based information sources. And the goal is to use this data in order to guide decisions about food security, market stability, economic progress, sustainability, and crop production. So here are some of the components of NASA Harvest. At the end, I'll put a link to the website for NASA Harvest, and please feel free to look at that link and see if there's any information there that's useful to you. NASA Harvest is made up of more than 50 members from different public, private, non-governmental, and humanitarian sectors. You can see the Grains Exchange here is one of the partners and one of the longest partners we've had in the NASA Harvest Consortium. We do have a number of partners across many different fields and many different sectors, and this gives us a wide range of expertise to draw from in order to provide the most useful information that we can. And I just briefly want to talk about how we work with the Grains Exchange. We have a pretty long relationship with the Grains Exchange, and we've had many fruitful projects with the Grains Exchange. The first one, I think the first one that comes to mind is the participation of Esteban and the Grains Exchange in the crop monitor for AMIS. So this is a monthly report identifying some of the strengths and weaknesses in crop production in several countries around the world for the main production and export countries. We've also worked with Esteban's methodology for creating winter crop maps, and we've done some validation work on that to see how accurate are the maps that the Grains Exchange is creating using the satellite information data. And as you see on the right, this is Esteban presenting that work at the American Geophysical Union meeting in Washington, D.C. recently. We also are working with the Grains Exchange on this Send to Agri pilot project to understand how does this cloud-based system allow us to map crop area and crop type within season in order to try to improve those estimates in any way that we can. And then lastly, we've gotten a lot of valuable feedback on this GLAM system that I'm going to be talking about in the rest of the presentation with regard to what are the features, the data, and the development trajectories that we take with that system. So we've had a very useful collaboration with LaBolsa. The GLAM system itself, I'm going to spend the rest of this presentation talking about. I think it's important to give some of the background on why we've developed this system the way that we have. Originally, the GLAM system was developed for the U.S. Department of Agriculture Foreign Agriculture Service, and the idea was to provide the USDA with moderate resolution data from the MODIS sensor to provide them with data that can be interpreted by specialists and non-specialists in order to assess crop conditions around the world in one easy-to-use tool. The GLAM system, as originally created, is a legacy tool. It's been under development for more than 15 years, but in some senses, the technologies have outpaced the system. So the technology for web services and for mapping has outgrown the abilities of the system to keep up over the course of 15 years. So while we're trying to be aware of this situation, we also have this opportunity from NASA, being that NASA is trying to move all of their data into the cloud, specifically into Amazon Web Services using a system called Cumulus. And under this project, they wanted to have prototypes of operational systems to understand what is the benefit or the cost of moving an operational functioning system into the cloud. And that's where we stepped up and decided to try to move this GLAM system into the cloud to test some of the capabilities, costs, and benefits of moving from a on-premises system using our own hardware into the cloud where we sort of pay as we go. So the components of this system, the first thing we have to do is provide near real-time information and near real-time processing of the NDVI products. NDVI is the Normalized Difference Vegetation Index, and it is essentially an indicator of crop health. It tells us how well the crop is progressing throughout the season, and it also gives us an indication of biomass, among many other things. We want to be able to process that data, but also visualize the data, to look at the data in either a map format or as a chart. And then to sort of make that information more useful, we provide these charting tools that you see the progression of the data of the index throughout the year to understand, is the crop doing better than normal, worse than normal? Is the crop delayed, or is it emerging early? And how is this responding to things like changes in rainfall? So the challenges that we need to address here, first, we have a long time series. We have over 20 years of MODIS data in some cases, with large volumes of data, so several terabytes of data. We have new data deliveries daily. Part of the challenge is taking in that new data every day and making sure that the data is processed rigorously so that the information is consistent from day to day. We have some difficult data formats to deal with, and then we also have the issue of quality. As you can see on the image here, a lot of the world is covered by clouds at any given point in time, and we need to be able to remove those clouds, understand where are the places where our data is not going to be as clean because we have a cloud obscuring the view of the surface, and where are places where we just have no information at all and the surface is completely blocked by things like clouds or aerosols like we're seeing on the west coast of the US right now. That said, if we can achieve this, the results are actually quite useful. So here we see some examples from the 2012 droughts across a lot of the Northern Hemisphere. And what we want to look at here is these charts on the bottom that show us the difference between the NDVI, so that vegetation index, for what is a normal year in blue versus the 2012 drought year in red. And we can see that the peak of that curve for those drought years is much lower than the peak during a normal season. And when this happens, we can use this as an indicator of a shortfall in production relative to what we consider to be normal, relative to a normal situation. In the US, this led to a decrease of 30% in corn production, 12% in soy production. And the effects in Kazakhstan and Russia were a little bit more dramatic with decreases in more than 40% of production. So if we zoom in here and we look at this European wheat belt here along the border of Kazakhstan and Russia, we can see particularly where some of these areas were harder hit versus others, and we can get that level of detail with the satellite imagery. So this means that we don't need to send people out to the field to monitor this. We can actually just look at the satellite image and get some idea of how well the crop is doing based only on the imagery that we can get every day. On the right-hand side here, we see some of the power of the time series analysis that we can do with this NDVI data. These are images from the old legacy GLAM systems. These aren't the new one yet. But we can see in the case of Sinaloa in Mexico, twice in 1 year, they had pretty drastic climate events. On the top, we see the evolution of a drought in Sinaloa, and you can see that the green here means the crop is doing well, brown and red means the crop is doing poorly. And as we evolve throughout the year, the color tends to get browner and browner, and then eventually they replant the crop, and we see that increase in the NDVI. On the bottom, we see a little bit more drastic effect. This is from a frost kill also in Sinaloa in the same year. And what's happening is the crop is progressing normally. We see a lot of green early in the season. And then once that frost event happens in February and effectively kills off a lot of the crop, we see the vegetation index decrease drastically, and we see it turn to that dark red. indicating that the crop is effectively failed for that year. So I mentioned before that we have an opportunity to re-engineer the system. We've seen some of the useful analysis that we could do with the old system, but the reality is that now our university and many universities are moving away from having their own equipment and hardware, and they're moving from their own data centers towards cloud solutions like Amazon Web Services, Google Cloud, and Microsoft Azure. NASA, at the same time, I had mentioned, is exploring the possibility of moving all of this data to the cloud, and we've used the GLAM system to explore those possibilities for improving the system and also reducing the cost. And I just want to note here that this is an excerpt from the minutes of the workshop on cloud computing and knowledge management that was held in Sanya, China a couple of years ago. Two of the key points were that, one, cloud computing is enabling big data analysis for agricultural monitoring, and two, increasing volumes of accessible data in the cloud is accompanied by a proliferation of tools. So whether we like it or not, doesn't matter how we feel about cloud computing, it's the future, and in some ways it's already here. So we need to adapt to this new computing reality. So just to highlight some of the benefits of this model, first, we've been able to take the GLAM system into a global system, whereas before we had regional windows where we could only see one country or one subcontinent at a time. Now we can look at the whole globe at one time and get a better understanding of what's happening in entire parts of the world. Second, we have cost effectiveness. I mentioned before that previously we had this system on our own servers. That server cost us about $100,000, and we can replace that large expense with a pay for what we use billing system, where if we don't have a lot of users one month, we don't have to pay for that capacity. It just sits there and we don't get billed for it. We have, most importantly, I think, the ability to do on-the-fly calculations. So rather than calculate the vegetation index for every city and for every state and every country, instead we actually are able to do this on demand, which means that we don't have to save all of the results. And this takes our data volume down from 300 terabytes to about 5 terabytes. So we're using about 2% of what we were using before, which saves us a lot on storage. And we can also apply color stretching, and this is important later, to allow the users to show narrower ranges of values. And this is really helpful for visualizing and understanding the data. And then lastly here, we're also able to calculate the statistics for regions that you draw on the map yourself. You don't have to rely on the system's regions as well. And one final note here, this system actually makes it easy for us to incorporate new weather variables, new crop health variables, crop mass, and statistical regions. This is much easier than it was before. And as we update these things, it actually means that we can customize the system more easily. So if we want to have a separate system for Argentina than we do for Brazil, it's very easy for us to implement that. So this is the first view that we have of the quote-unquote new GLAM system. The data that we have in the system, we've retained that vegetation index variable. So we have the NDVI from two different sensors. We're working to incorporate a new sensor from NASA soon. Hopefully this will be done in the next month or 2 months maybe. We've expanded the data to also include these weather variables. So we have precipitation data that comes from the Climate Hazard Center at University of California, Santa Barbara. We have 2 different versions of this product. So this is just an indicator of how much rainfall has occurred over the last 10 days. We have the soil water index from the Copernicus program in Europe. This is an indicator of how much water content is actually in the soil, also over a 10-day period. And then finally, we've integrated the temperature and precipitation models from NASA's MERA reanalysis data set. And for this, we keep the minimum, maximum, and mean value for the temperature. This is to give you an idea of whether you need to be wary of something like frost or whether you have excessive heat in an area that could adversely affect the crop. So just to give an example of how these data can be used, this is an example of the recent winter wheat conditions in Cordoba in Argentina. Here we're looking at the soil water index on the bottom left. And we see that in general in South America, the conditions are red. So we have a low soil water index for a lot of the area. But what we can do with the system is that we can focus on only the areas that are producing winter wheat in this case. So here in the circle, we've on the bottom right-hand side, we've removed all those areas that are not known to grow winter wheat. And if we focus in on that Cordoba area, we can create a chart like the one we see on the top, showing that in orange, the soil water index for this year is rather low compared to previous years. And once we start to understand that we have a low amount of moisture in the soil, we know that that's going to negatively impact the crop. We can start to look at the vegetation index and start to see what is the effect of this lack of soil moisture. So here on the bottom left, we see the NDVI. This is again that indicator of the crop health. On the bottom right, we've removed all of the non-cropped areas from that map. And on the top, we see that the value in orange for this year is significantly lower than what we expect based on that mean value and the comparison to last year. And what this lets us say is that, first of all, the conditions are worse than last year, so we have a reference point from the previous year, but we also have a reference point for the average over the last 10 years. So we can put some context into these numbers to understand, even if we don't know that 0.3 NDVI equals a certain amount of tons per hectare, we know that it's better or worse than the previous year, and that's a useful reference point in and of itself. And what we see from this is that even though the dry conditions have led the index to be lower than usual, and they're among the lowest that we've seen in the past 10 years, we still do have plenty of time for the crop to recover because we're not really into the growing season yet. It is early and the plant is perhaps vulnerable. But where we really need to start paying attention is when that value starts to increase in January, February, and the crop really starts to increase in biomass. So this is sort of a simple example, but we also have other capabilities in the system as well. We can use the crop mass to limit the area of analysis to only the planted areas that we just saw. But more importantly, we can compare long time series. A lot of these variables we have over 20 years of data for, so you can compare it to any point in the last 20 years to see how are we doing relative to previous seasons. And we can create this concept of analog seasons where we know that a similar thing happened in the past, and we can see what happened when we had that event in the past and how do we expect it to be either repeated or different from what we see this year. I didn't show it in the example, but we can also map different variables in the same graph. So in that example that we looked at the rainfall and soil moisture versus the vegetation index, we could actually plot the soil moisture and the vegetation index on the same graph and see what is that lagged effect of the lack of rainfall and the health of the crop. We can also change the starting period of the maps. In the previous example, I didn't start the season in January because that wouldn't make sense because that's sort of the middle of the growing season. Rather, we offset it to October and November, and that lets us see from when approximately the crop was planted to throughout its actual growing season rather than cutting the season in half. And then lastly, the data that we saw in those charts before can actually be downloaded and you can use it in Excel and bring it into other software packages to do your own analysis on it. You don't have to rely on just our tools to do this. You can export it into your own environment and do the analysis that way. So I think lastly here, I just want to talk about some of the improvements that we have coming to the system in the near future. The big one, I think the one that is perhaps most exciting is that we are trying to integrate forecasted data into the system, and we've identified 3 data sets that we think will do a good job of giving different outlooks into the future. So first, we want to bring in the GEFS model, the Global Ensemble Forecast System. This provides the forecast for up to 16 days into the future, daily forecast. So this gives you an idea of the near-term forecast for temperature, precipitation, and soil moisture. Beyond that, we're looking at a data set called SubX, the Subseasonal Experiment. This is not an operational product. This is experimental, but nonetheless, it gives us a 3 to 4 week outlook. So it gives us a monthly forecast of what we expect for temperature and precipitation. And then finally, we are looking at a long-term seasonal forecast for up to 6 months out into the future from the NMME model. This is giving you precipitation and temperature. This one is a little bit difficult to use because the scale or the accuracy of the forecast depends on the time of year. So there are certain cases where you would and would not want to use this depending on what month of the year it is. So we're trying to work out some of the details on how to provide this to users in a way that is easy to interpret and not misleading. And with that, I will conclude. Thank you very much for listening to my presentation. If you're interested in more information, please go ahead and go to our nasaharvest.org website, and the link for the GLAM system that I presented is also available here. It's glam.nasaharvest.org. Thank you very much.
Thanks, Mike. I think that the GLAM system is an incredible tool. Indeed, we are using a lot during our day-to-day analysis. During this season, we are registering important losses of crop condition due to extreme dry conditions, as you showed in the central part of our agricultural area. No, Córdoba is mainly affected by extreme dry condition. It's also affecting the crop condition, the wood condition. So we are expecting losses on yield. And related to that, Mike, you presented a lot of weather data, no? And do you think is it possible to develop a productivity index and add it to the GLAM system on a large scale?
I think so. I think in theory it is possible, and we have the data to do it. I think that this is also something that's very sought after by a lot of companies at the farm level in particular, because a lot of farmers want to have just one number saying how well are they doing. And this is true for things like sustainability, not only the crop productivity. But I think at the larger scales, at the provincial to country levels, I think this is also something that's useful. And it is work that is actually being done at UMD. We have several people actually working on that, and Ritwik Sahajpal in particular is working on incorporating things like these weather forecasts into his within-season crop condition and crop yield models. So it's very interesting and I think promising lead. One thing that has to kind of be kept in mind here is what is the error tolerance that people have, and that's going to depend on the country. It's going to depend on the region. Some places 5% error is okay. Other places 20% is okay, and the amount of error that you have in that estimate is really going to be determined by the people who are using the estimate. We also have a lot of variability from region to region. I think there's probably no one-size-fits-all solution. Some ecosystems are going to be water limited, and others going to be energy limited, for example. So the variables are not going to respond in the same way in every region. I think that's where methods like machine learning really kind of help, because they give you a sort of more regionally adaptive solution that identifies what are the more important variables in this area versus another area. So I think it's something that's possible. I think it's something that hopefully we can integrate into the system soon. And I think it's a very promising and useful data set that has to be kind of, we have to understand how to use it before we really integrate it into the system. But I think it is the way that we're going.
Okay, thanks for that, Mike. Finally, I would like you to tell the audience how much does it cost to the University of Maryland to run this whole system. I think a lot of people will be amazed about this.
Sure. So I mentioned that before, the system that we were using, just the hardware, so just the computer itself, costs about $105,000 to purchase. And that's because we were using a lot of storage. We needed 300 terabytes of space, which is a very significant allocation for disk space. Because of the way that the cloud works and how we can scale things out and break things into small chunks and use a lot of resources to compute things, and because we only pay for what we use, we can reduce that 300 terabytes of storage down to 5 terabytes of storage and then just compute the results whenever people want them. And because we don't have to have this computer running all the time when we're not using it, our monthly cost is actually only about $400 per month, which means that our break-even point for this system with our current usership is about 20 years compared to the system that we purchased. But it's 20 years, but it's not really 20 years because we have to replace that system every 5 years. So in theory, we would never actually catch up to the cost of having the system on our campus unless hardware costs really went way down. And also, what's worth keeping in mind here is that even though our costs are lower, and that is certainly something that is a goal of this system, we're able to do so much more with the data that we have because we can compute all of these statistics on the fly, and because we can be more flexible. We're spending less money, but we're also doing a lot more. We have a lot more data. We have more flexible analysis capabilities, and we can look at the whole globe instead of a regional window at one time. And then also, I guess to add to the question, that's the cost to UMD. We also work with regional partners to set up specific systems for national. For example, we're working with CONAB in Brazil, and they have their own of regions and crop masks that they want to use, and they want to limit their analysis to just the places that they're interested in. And with this system, we can do that fairly easily. The cost for us is almost negligible because we aren't spending a lot of money recreating the data. They can just use the data that we already have. So I think that's another huge benefit of the system, is that for every user that we create a new version of the system for, the cost is very low as long as you're okay with using the data that UMD is hosting.
That's incredible. Thanks, Mike. Okay, that was Mike Humber from Maryland University sharing this incredible tool for all the analysts around the world that need to analyze weather condition on a global or provincial scale. But now it's time to talk about forecasting yield, no? Because we talked about planted area, weather condition during the crop cycle, and how the weather, how you can assess the impact of weather during the in the planted area from the planting period until the harvest period. But now we are at this stage of the cycle when we have to forecast yield, no? We have defined our planted area and how the weather impacted on it. And now we need to forecast yield. And thanks, we are lucky we have Belén Franch that is going to answer this question: how to forecast, objectively forecast the crop yield on a large scale or in a plot scale. Let me introduce you to Belén. Belén Franch is a doctor cum laude in physics from Department of Física de la Tierra y Termodinámica of the University of Valencia. From 2013 to 2019, she worked as an associate research professor at the University of Maryland and as a research associate at NASA. Since 2019, she has been working at the Universitat de València as a distinguished researcher and at the University of Maryland as Adjunct associate professor. Her main line of research focused on the use of remote sensing satellite imagery to analyze the Earth's surface. Currently, Belén leads the working group of crop yield estimates within the international consortium NASA Harvest, founded by NASA. And since 2019, she is a member of the GeoGLAM initiative. In 2018, Belén Franch was awarded by NASA with the Early Career Achievement Medal. So it's a pleasure to have you here in this panel, Belén. Now let's pay attention to Belén's presentation.
Yeah, thank you so much for the very nice introduction, Esteban, and congratulations, Mike. It was a great presentation. I really love seeing how everything is evolving so well. So I'm gonna switch to Spanish then.
Yeah.
Vale, pues muchas gracias a la Bolsa de Cereales por invitarme a participar en este panel. Mi presentación va a centrarse en la monitorización del rendimiento agrícola mediante teledetección desde nivel global a nivel de campo, a nivel de parcela. Yo, como bien ha dicho Esteban, trabajo en la Universidad de Valencia como investigadora distinguida y profesora universitaria, pero sigo asociada a la Universidad de Maryland como profesora adjunta. También estoy liderando la iniciativa de Yield Monitoring o del seguimiento de rendimiento mediante teledetección en NASA Harvest y también sigo asociada a NASA. Mis coautores también pertenecen a estas instituciones, por lo tanto quería hacer hincapié en eso. Bueno, como bien ha introducido antes Mike, la idea de poder predecir o poder proporcionar información objetiva lo más pronto posible en lo que es la campaña agrícola es muy importante, es uno de los principales objetivos de GeoGLAM, la iniciativa lanzada por el G20 para facilitar o promocionar la información a través de satélite lo más temprano y objetivamente posible. Y todo esto se basa en mejorar toda esta información debido a que, en general, cuando se hace un pronóstico de cuál va a ser la producción de los principales cereales producidos a nivel mundial, los precios del mercado de alimentos siempre va ligado de alguna manera a estos pronósticos y sobre todo si hay alguna crisis en alguno de los principales países exportadores de los principales cereales y como se ve en esta gráfica. Por lo tanto, mediante teledetección lo que hacemos es hacer un seguimiento a los cultivos. En esta imagen se puede ver una imagen de relativamente alta resolución, donde se pueden ver los diferentes campos. En rojo se ven los campos sin vegetación, suelo desnudo, y en verde, conforme va aumentando el verde, es que va aumentando la biomasa. El NDVI, que antes ha nombrado Mike, es un indicador de la cantidad de vegetación que hay, o también el estado de esa vegetación. Por lo tanto, con esta base de el seguimiento de los cultivos, podemos al final llegar a aplicaciones directas, como por ejemplo el análisis de los diferentes cultivos, la distribución de estos cultivos, podremos hacer una estimación del área, en qué condiciones se encuentran estos cultivos, también cómo varían sus ciclos de crecimiento y finalmente una de las principales aplicaciones y en la que me voy a centrar yo en esta presentación, podemos estimar y predecir cuál va a ser el rendimiento. Pero todo esto son la aplicación final. Nosotros con teledetección no medimos esto, sino que medimos la biomasa pues a través de índices de vegetación como el NDVI, podemos medir la temperatura superficial de la planta, evapotranspiración, humedad, diferentes variables meteorológicas, etcétera. Por lo tanto, nuestro objetivo, nuestro papel en todo esto es buscar un vínculo, o sea, de entrenar modelos o desarrollar modelos que puedan, a través de datos de satélite, permitirnos realizar todas estas aplicaciones. ¿Vale? Entre cuál es la mejor o cuál es el mejor satélite o cuál es la mejor imagen de satélite para desarrollar estos estudios, pues todo depende de la aplicación que vayamos a realizar. Obviamente hay diferentes tipos de satélites, satélites de baja resolución, como este que vemos aquí, llamado MODIS, es una de las misiones más importantes de NASA. Es baja resolución, vemos que aquí pues tenemos píxeles que cubren áreas muy grandes, en este caso son 250 metros, pero pueden llegar hasta los 5 kilómetros. La ventaja de estos sistemas es que pasan muy frecuentemente, tenemos 2 imágenes al día y además cubres fácilmente todo el mundo, ¿no? No tienes imágenes pesadas que cuestan mucho de procesar, sino que son mucho más fáciles de trabajar a nivel global. ¿Vale? Luego tenemos imágenes a resolución moderada, como Lanzamiento o Sentinel-2, y luego imágenes de alta resolución o muy alta resolución, como Rapid Eye o Planet. ¿Vale? Vemos que en función de cada uno de los satélites vamos a tener una mayor resolución, vamos a ver mejor nuestra parcela o el área que vamos a estudiar. ¿Vale? En un primer momento voy a centrarme en baja resolución. ¿Vale? Entonces, ¿cuál es el problema que tenemos a baja resolución? He hablado de las ventajas, ¿no? Pasar 2 veces al día, una alta frecuencia de paso, lo que nos asegura tener todos los días imágenes, un seguimiento muy rutinario de los cultivos y una fácil cobertura global. Pero el problema es que tenemos píxeles mixtos, no observamos el cultivo que nosotros queremos analizar, sino ves una señal heterogénea, mezclada pues con los cultivos circundantes o las superficies de suelo desnudo o bosques que tengas alrededor del cultivo que tú quieras analizar. Por lo tanto, para ello es esencial utilizar máscaras de cultivos o mapas de clasificación que nos digan dónde se encuentran estos cultivos. En este caso, que es un ejemplo en Kansas, de un condado en Kansas, es un mapa de clasificación que nos dice en este condado por píxel qué porcentaje de trigo tenemos. Dentro de ese mismo píxel, si tenemos un 100% de cultivo de trigo o si es trigo y algo más, ¿no? ¿Qué porcentaje de trigo hay? Entonces, en 2019 presentamos este método, el método ARIA, en el que nos centramos en extrapolar, en extraer la información, dejar solo la información que nos proviene de nuestro cultivo que nos interesa analizar, en este caso, pues trigo, ¿no? Pero lo que hacemos es dejar la señal pura a través de métodos de unmixing o no sé cómo decirlo en castellano, pero bueno, espero que me entendáis, que lo que hacemos es desagregar toda la información espectral que nos llega de otras superficies, ¿no? Y dejándolo solo el trigo o el cultivo que vayamos a analizar. A continuación, una vez tenemos la señal que nos proviene solo del cultivo que queremos analizar, analizamos su evolución temporal. Como bien ha enseñado Mike antes con el método GLAM, hay una relación prácticamente directa entre el pico del índice de vegetación o de la evolución del cultivo durante el año con el rendimiento final, con cuán saludable esté o con cuál va a ser su producción final, ¿no? Cuanto más alto es el pico, mayor rendimiento, si es menor, peor rendimiento, ¿vale? Pero aparte de eso, aparte del pico en sí, también descubrimos que la anchura del pico, o la anchura, cuánto dura este pico en el tiempo, también está relacionado con el rendimiento final. Y finalmente, aparte de eso, si ocurre alguna condición de estrés hídrico después de que haya pasado el pico, para eso incluimos las variables que miden la evapotranspiración, es decir, la evaporative fraction o fracción de evaporación, ¿vale? Entonces, nuestro modelo se basa principalmente en esos 3 parámetros. O sea, primero lo que hacemos es desagregar toda la información que llega desde nuestro cultivo mediante estos métodos de unmixing que he hablado, y luego analizamos el pico, la duración del pico, el valor del máximo del pico, y aparte corregimos mediante la fracción de evaporación durante 30 días después de que este pico se haya producido, por si acaso ha habido algún estrés hídrico que no haya capturado este índice de vegetación. Todos estos 3 parámetros los correlacionamos finalmente a través de una correlación lineal calibrada con datos estadísticos oficiales a nivel de subnacional. Y esto nos muestra los siguientes resultados. Aquí podemos ver la validación a nivel subnacional en 7 países de los principales países exportadores de trigo a nivel mundial. Se cuentan alrededor de un 70% las exportaciones de trigo según las estadísticas de 2018. Y podemos ver que a nivel subnacional estamos consiguiendo un error de un 15%, mientras que a nivel nacional el error es en torno al 7%. Esto, la verdad es que son buenos resultados para un modelo básicamente utilizando datos de teledetección. Pero ¿cuál es el problema? Que nos tendríamos que esperar a que este pico ocurriera o incluso que pasaran esos 30 días para corregir los efectos de estrés hídrico. Y vemos que en este mapa, en que muestra el punto o la fecha en que se da la maduración del trigo a nivel global, que dependiendo de dónde te encuentres, incluso dentro de un mismo país, esto ocurre en diferentes fechas del año. Por lo tanto, para evitar tener que esperarnos a que todas las divisiones subnacionales o todas las provincias, condados, etcétera, lleguen a ese punto, lo que hicimos fue en 2015 propusimos un modelo basado en la acumulación de los grados de temperatura. He sabido que tanto el trigo como el maíz son plantas, son cereales que depende su desarrollo fenológico de la temperatura acumulada, ¿no? Cuando acumulan cierto nivel de temperatura, entonces la planta pasa a un estado fenológico más avanzado, ¿no? Entonces, basados en este principio, lo que hicimos fue analizar cómo va evolucionando la planta, cómo se va desarrollando el índice de vegetación a lo largo de la temporada, ¿no? Aquí en este ejemplo es un condado de Kansas en el que podemos ver que en el día 120 de este año la planta, o sea, el pico parece que ha ocurrido, pero aún es muy temprano como para saber qué forma va a tener esto, ¿no? Qué evolución va a tener, ¿no? Por lo tanto, lo que hacemos es ajustarlo a una forma gaussiana, utilizando como base para ayudar al ajuste pues la media de las condiciones de suelo, ¿vale? Esto simplemente es un cálculo matemático para ayudarnos a forzar el ajuste como método gaussiano, ¿no? Conforme avanzamos en la temporada, vemos que la gaussiana va completándose y, por lo tanto, tenemos una mejor estimación de los parámetros, que esto sería el pico de la gaussiana, el pico que nosotros estamos utilizando en el modelo, o la amplitud, la anchura de la gaussiana, ¿vale? Por lo tanto, ahí tenemos ya datos que finalmente, una vez se completa el ciclo, ya podemos utilizar los datos verdaderos para el modelo. Vale, pues con este ejemplo podemos ver cómo hemos ido aplicando el pronóstico, ¿no? el modelo de forecast, de predicción, a los diferentes países que había mostrado anteriormente, ¿no? En esta gráfica el color rojo muestra la validación subnacional, en negro tenemos la validación nacional y la línea discontinua muestra la mejoría del modelo, la mejoría del error en función del día del año cuando utilizamos datos térmicos, es decir, cuando corregimos por condiciones hídricas. Ahí utilizamos la diferencia entre la temperatura del aire y la temperatura de la superficie. Es algo que estamos implementando hoy no quería meterme demasiado en tecnicismos, ¿no? Pero bueno, la idea es que con este modelo podemos producir una predicción fiable, eso se refiere a entre un 4 y un 10% de error a nivel nacional y un 8 y un 20% de error a nivel subnacional. Y entre un mes y un mes y medio antes del pico de la vegetación, la maduración, que eso significa unos 2 meses y medio aproximadamente. El otro día hablando con Esteban me dijo que tal vez 3 meses antes de la cosecha, por lo tanto es muy buen resultado. ¿Vale? Esto es a nivel de baja resolución, a nivel nacional y subnacional. Pero si utilizamos otro tipo de datos de satélites, los de resolución moderada, ya pasamos de ver los campos conforme hemos visto aquí, que son píxeles muy grandes, a tener una mayor resolución y poder aplicar estos modelos a nivel de parcela, ¿no? Entonces, aquí tenemos un ejemplo que desarrolló mi colega Sergi Skakun de la Universidad de Maryland, donde con datos que tenemos de parcela en Ucrania pudimos entrenar el modelo utilizando Sentinel-2 y Landsat. Son dos satélites, Landsat pertenece a NASA, Sentinel-2 a la Agencia Espacial Europea. La combinación de ambos nos permiten observar la Tierra con unos entre 5 o 7 días de tiempo, ¿no? de frecuencia. Por lo que tanto es una buena solución mezclar ambos satélites. Es un proyecto que estamos desarrollando también en NASA. ¿Vale? Y entonces, utilizando los datos de parcela, podemos calibrar el modelo y también poder obtener datos de rendimiento a nivel de parcela, ¿no? Incluso más o menos ver qué forma va a tener el rendimiento dentro de la misma parcela. Esto es un resultado que he desarrollado ahora aquí que estoy en Valencia, donde pues el cereal más predominante es el arroz. Quería mostrar también resultados sobre otro tipo de cereal para mostrar también la aplicabilidad de este método a otro tipo de cereales. En este caso dispongo de unas estadísticas que me pasaron desde un instituto valenciano de investigaciones agrícolas. Son muy fiables y esto nos ha permitido desarrollar un modelo con bastante... O sea, faltan muchísimos más datos estadísticos, pero es un buen comienzo. Nos está mostrando que hay una cierta correlación. Estamos hablando a nivel de parcela, no a nivel nacional, por lo tanto, tener un error a nivel de parcela de un 6%, la verdad es que es un buen resultado. Obviamente, conforme vayamos completando la serie de datos, podremos desarrollar modelos más robustos, basados en más datos estadísticos. Y luego quería mostrar esta aplicación también, que aunque no sea estrictamente de rendimiento, también nos muestra una aplicación muy buena de la teledetección. En este caso, un agricultor contactó con nosotros porque quería, en un campo que tradicionalmente había plantado avena, plantar almendros, ¿no? Entonces, antes que nada, quería que estudiáramos si el terreno tenía algún problema y así poder decidir qué zonas plantaba de almendros o no. Entonces, estuvimos analizando históricamente cuál había sido el rendimiento del cereal en esta parcela, mirando mapas de anomalías, y pudimos ver que había una zona, sobre todo aquí al norte, en que parecía que el rendimiento o que la tendencia de la vegetación era peor que los demás zonas de la parcela. Y analizando el perfil de la inclinación, pudimos ver que estaba directamente relacionado también con la inclinación de la parcela y, por lo tanto, esta zona más hacia el norte no era recomendable plantar los almendros ahí. Por lo tanto, vemos que podemos realizar muchísimas aplicaciones de gestión de agricultura de precisión, por decirlo de alguna manera. Finalmente, quería acabar con la aplicación de imágenes de muy alta resolución. Este es un trabajo que ha desarrollado mi colega Sergi Skakun de la Universidad de Maryland, en el que contratamos datos a nivel de tractor. Conforme la segadora va pasando, va proporcionando datos de cuál es el rendimiento a cada metro o 3 metros, no sé si exactamente. La cuestión es que esto es una imagen directamente de la cosechadora, del rendimiento proporcionado por la cosechadora, ¿vale? En este caso, los datos más azules son de mayor rendimiento, ¿no? Y los rojos de menor rendimiento. Si vamos agregando la información que esta cosechadora nos va dando a resolución de Sentinel, que son 10 metros, vemos que más o menos seguimos viendo las variabilidades del rendimiento. Pero cuando ya nos vamos a resolución Landsat, que son 30 metros, estas diferencias ya se minimizan. Por lo tanto, de ahí la importancia de utilizar datos de cuanta más resolución posible, mejor. Y luego, finalmente, pudimos ver que hay una cierta correlación entre las imágenes que observamos mediante satélite. Esta es una imagen de Planet, aquí a la mano derecha, de 3 metros de resolución, y podemos ver que a finales de agosto, estamos hablando de unos 2 meses antes de realizar la cosecha, ya podemos observar las características, la variabilidad del rendimiento que luego la cosechadora nos mostró mediante los datos durante la cosecha. Por lo tanto, ahí vemos un campo a desarrollar muy interesante. Si tuviéramos, y estamos trabajando en tener acceso a más datos de este tipo para así poder entrenar mejor los modelos y poder desarrollar mejor esta aplicación. Pero los primeros resultados son muy prometedores. Por lo tanto, quería acabar la presentación con unos take-home message o mensajes finales. Hemos visto que la teledetección va a jugar un papel fundamental en la modernización de las técnicas agrícolas. Eso yo creo que es algo que todos podemos estar de acuerdo, ¿no? Tanto NASA, las grandes agencias espaciales como NASA o la Agencia Espacial Europea están mostrando unos claros planes de continuar y seguir reforzando las misiones tanto a alta como media resolución. Y seguir dotando de más satélites para aumentar la frecuencia de paso de estas misiones e incluso adquirir o hacer disponible al público imágenes de alta resolución como Planet y etcétera. Seguimos en búsqueda de una mayor precisión a nivel de campo. Para eso, quiero insistir, necesitamos datos y aprovecho esta plataforma para cualquier agricultor o agencia o institución que pudiera proporcionarnos de datos es algo muy buscado, nos nutrimos de ellos, así que necesitamos datos estadísticos fiables y esto lo que nos permitirá no solo es mejorar los modelos a nivel de aplicaciones agrícolas de alta resolución, o sea, de ayudar al propio agricultor a gestionar mejor su campo, sino que también nos permitirá proporcionar mejores resultados a nivel subnacional y a nivel nacional. Con eso ya finalizo mi presentación.
Gracias, Belén. Let's switch to English so Mike can understand. I think that, okay, this is an incredible work also, and it will help, no doubt that this kind of work will help during the making decision process of our producers around the world, no? Because if you can early predict your yield potential, you can take decisions apart from that point on. Okay, but I would like to ask you, Belén, what happened to the model when you have to work in a cloudy season? Does this model work with radar images or just with optical sensors? Because this is an important issue. The clouds are an important issue for optical sensors.
Yeah, so far we're just basing our model on optical and thermal data, but I mean, because we are so far we are applying it over regions where like clouds are not a major problem, like southeast of Asia, where we will have a problem for sure. So so far we're using optical data, but I mean. When we should be working, or we are looking for like training a relationship between optical and radar data, so we can also implement that technology in areas where we have difficulties of images or like observing the surface when using optical data. So for sure, it's one thing to be developed in the near future.
Okay, that's great. That's great. And I think that this will represent an important improvement to the model also. But finally, the second question I wanted to ask you is, you can early predict the potential yield of a crop during maybe the middle of the crop season, make an early prediction of the yield potential. But what happens if after that point you register a frost, a flood, or an hailstorm that produce damages and negatively impactly in the yield potential of the crop? Can you measure the impact of these weather variables in terms of yield potential?
Yeah, I mean, so far we are taking into account any drought or like any stress, water stress. We using the thermal like measurements, But regarding other variables, the problem that we have when we are implementing these empirical models is that we need those events to have happened in the past. So we have to train our models with past events. So that's the point, that we need representativity or like a statistically significant evidences of how the different variables are like related, or like how the different events affected our area. So that's the problem, and that's one thing that we are developing in one project using like past events like AVHRR that's going back to the 80s, trying to learn from the past so we can like implement or train our empirical models with extreme events that happen in the past that are not so frequent, but sometimes like suddenly happen in a region. So that's the point.
Okay, yeah, it's clear. Thanks, Belén. I think your work is incredible, and hopefully your model will help us to objectively improve our yield forecast on a large scale. And this is a huge improvement in our work at the Grain Exchange, but also for all the people that have to take decisions looking into this kind of variables. Finally, I would like to ask you both guys the final question, and it's about the future of this technology. Where is the scientific community pointing right now, and what limitations do we have to face in order to continue moving the frontier of these technologies?
Mike, you can start first.
So I think the biggest challenge, but also the biggest opportunity, is going to be the volume of data moving forward. We have new systems coming out like NISAR that's expected to generate more than 2 petabytes of data per year. This is data that you can't process on your own hardware. You need to use bigger computing solutions like things in the cloud or like high performance computing resources. The opportunity here is that a lot of those resources are starting to come down in price at the hardware level. So hardware isn't a challenge anymore. Even at the consumer level, this week even we've had the launch of the new NVIDIA and AMD GPUs that can greatly speed up the progress with deep learning and machine learning. And the price of those have actually been cut by a factor of 6 compared to the previous generation. So we have easier access to the hardware you need to compute this volume of data, but we also have more accessibility in terms of things like the cloud resources that you can rent. So these are big opportunities where we have a lot of data, but we also have the hardware catching up that lets us interact with those data. With NASA Harvest and the GLAM system, we are starting to put an emphasis on making sure that our data is ready for machine learning in order to handle that volume of data. So there's been a lot of talk recently about what's called analysis-ready data, which is data that's processed in a way that you can immediately put it into your workflows. We're trying to move that a little bit further and generate the data in a way that you can immediately ingest the data into your machine learning workflows. And hopefully by doing that, we can accelerate the rate at which people can produce scientific results from the data. This is something that we want to do for the data that we already have. We also want to do it for the forecasting data that we're planning to integrate into the system. I think in order to make this more useful, though, we also need more information from the ground level, like Belén was talking about. How do we train the models to ingest this data? And part of it is better understanding the data and the methods we're using now, but we also need to better understand more variables surrounding the crops themselves. I think not many people would disagree that we don't know a whole lot about soil and how that interacts with crops and nutrients and things like that, especially from the satellite remote sensing perspective. So if we can have more information about things like that, better understand those variables, better understand things like when is the plant most vulnerable, and use that to identify portions of the season during which, if we have a drought or frost, when is it more likely to affect the plant negatively than other points of the season. Those are the types of data that we need moving forward in order to really kind of maximize the new information flows that we have coming in from a number of sources.
Yeah, I mean, I don't have anything more to say. I think you covered all of it. Yeah, I just to insist, as I said during my presentation, like we need more data, we need ground data, and Mike also insisted on that, and that's a major thing. And that, of course, as Mike has stated in his very nice remark. It's like the issue right now is we are getting into an era with like tons of data, tons of variables, tons of availability of everything. So yeah, of course we have to evolve into a cloud environment, and yeah, I think that's absolutely the future. So let's see how everything goes.
Okay. Yes. It's good to you take advantage of this presentation in order to invite people to share data that helps to improve the accuracy, not only the accuracy of this model, but also to improve the amount of variables that you can analyze through remote sensing technologies. And this is very important, and I'm happy that you can use this space to not only to show your work that is amazing, but also to invite people to participate with you, to collaborate with you. Now, wrapping up, I would like to share with the audience some conclusions. At this point of the panel, I think there is no doubt that the incorporation of these technologies represent a significant contribution to the agricultural activity. We at the Grain Exchange are already working with these technologies. The GLAM system has become an important tool of our day-to-day analysis. It's critical today, for example, to analyze what is happening, how the drought is affecting winter crops, and how the same weather issues are going to impact also in the near future in the planting of the summer crops. For example, Jordan's preliminary result on the development of the ag region also helped us to better understand the ag planted area and on a national scale. And that was amazing because allowing us to make some correction when you are overestimated or underestimated the crop area, a regional scale or in a national scale. This is important. His preliminary result helped us to make some correction. Some of the correction we presented this morning are due to this preliminary result Jordan shared with us. Finally, we are working with Belén, sharing local data in order to improve the accuracy of her model in Argentina, and this will be an amazing tool that will also help us to improve the production prediction of each crop during each season. So I'm very glad, I'm very happy to have spent this time with you guys. I'm really a fan of your work. You already know that. I wanted to finally to thank Belén, Mike and Jordan for spending the time to share your work with this audience. It was a pleasure to spend this time with you guys. If anybody is interested in contact them, you can send them an email. Thank you very much. I hope to see you soon, and take care, and hopefully you will be okay and healthy, stay healthy and far for this COVID situation. Thanks, guys.